If your vLLM p99 latency is 5 to 10 times worse in production than in benchmark, it's not your hardware but your line management. One long prompts prefill is blocking every other token generation and your average is hiding it. You don't fix it by buying a bigger GPU, you fix it with chunk prefill, the right scheduling policy, and a benchmark that actually looks like real traffic. That's the whole video, now let me show you why. Picture the fast lane at the grocery store. You have got one carton of milk, the person ahead of you rolls up with 200 items, and everyone behind them just stops. If you ask the store their average checkout time, they would probably say something around 90 seconds, a real number, but it is useless to you because you're the person who's behind the cart. Your inference server works exactly like that lane. Same model, same GPUs, same code, that benchmarked fine, real traffic showed up, and your P99 fell apart. Your test wasn't wrong, it was just too clean. In an LLM server, works come in two different sizes. Generating one token decode, it is the milk carton shopper, quick and light, reading in a long prompt before you can answer. Prefill, it is the overflowing cart. It gets processed in one big go, and while it does, the quick shoppers behind it wait. Requests 1, 2, and 3 are streaming tokens to the users. Request 4 arrives with a long prompt. Its prefill runs as one block and the other three freeze. They did nothing wrong, they are just stuck behind the cart. This isn't a rounding error. The Sarathi researchers measured that a single prefill sharing the batch can push time between tokens up by as much as 28x versus a batch doing only decode. That's the entire reason your average looks healthy while one unlucky user watches the response hang. Partly, the old way static batching made a whole lane wait until every person in it finished before anyone new started. Continuous batching fixed that. The moment a shopper finishes, they leave and a waiting shopper gets waved in. Big win, and if you run vLLM, you already have it. But notice what it didn't fix. Waving people in and out faster does nothing about the cart. The cart still lands in a lane and the lane still jams. Because continuous batching still tends to ring up the whole cart in one uninterrupted go, we made the rest of the store faster and the jam, but the jam is still there. Here's the fix. Instead of scanning all 200 items before helping anyone, you scan a handful, pause to ring up the milk, scan a few more, ring up the next quick shopper, and alternate. The cart still gets done, but nobody behind it waits forever. That's chunked prefill. You slice the long prompt into chunks, and each round you process one chunk to the next to the decode steps already running. The stream stays smooth for everyone. In the Sarathi serve tests, handling prefills this way let a server absorb up to 2.6x more traffic at the same latency target on a smaller model and up to 6.9x more on a much bigger one at the same hardware. You just stopped letting the cart block the lane. One tile matters the most and it's an honest trade-off. How many cart items do you scan before you move to a quick shop? In vLLM, that's called max num batch tokens. Scan too few and the milk shopper is excited. But the cart that has the most number of items takes longer to scan and now that shopper is waiting forever. But if you scan more items in the big shopper's cart, then you make everybody wait. Researchers usually test it with numbers like 512 and 2048, but you need to test it on your own traffic. Quick myth, because a lot of explainers get this wrong. You will hear how page attention fixes latency. It doesn't, because it fixes memory. You will be reorganizing the entire bag room and fitting each shopper's bag with more stuff without spilling it. That helps, but indirectly, because now you can fit more shoppers at once. The cashiers aren't forced to keep the lane tiny and they have more freedom to decide how they interleave. So paged attention doesn't decide who goes first, it decides or it helps in setting up the table. It's chunk prefill and your scheduling policy that actually manages the line. So who does goes first? That's your scheduling policy. The default first come first serve is one big fair queue, which is fine until a clump of giant cars arrive together and everyone's wait blows out. Priority is an express lane. Sudden requests jump ahead. SLA aware is a manager working the floor to hit a wait time target instead of just taking people in order. And here's the part that quietly owns your tail. When the registers get overwhelmed, the store sometimes pulls a half-finished shopper out of the line to deal with later. In vLLM, that's preemption, and recovering that request means redoing its work or reshuffling its data out and back. It's rare, but rare and painful is what exactly P99 measures. The average shopper never gets pulled. The one who does is the story your users tell. Control P99 by controlling who gets pulled and how often. Back to the benchmark that said everything was fine. It lied because it was the store at 6 a.m., evenly spaced shoppers, all about the same number of items, one at a time. Real traffic is Saturday afternoon. People arrive in clumps, and carts range from a stick of a gum to a month of groceries. The search engine study found real request arrivals are bursty enough that an even test pattern doesn't describe them at all. Burst GPT showed the same across more than 10 million real requests, sudden pileups in how many requests are in flight at once, and pileups are exactly when cars stack up and jam the lanes. The test worth running is simple. Take one setup, run it under a tidy even load, then replay a real bursty pattern through the exact same setup. And look at both. Your average barely moves, your P99 jumps. This gap is the whole game, and it's the past or no benchmark bothers to show you. Before you touch anything, figure out which jam you have. Long prompts, short answers, RAG, big system prompts, you are prefill-bound, chunk prefill is your liver. Long answers, you are decode-bound, look at the batch size and memory room. Average is fine, but the tail fails apart under bursts, you are scheduling bound. That's a policy and preemption problem. Then, in order, turn on chunk prefill if you have long prompts and a tail problem. Tune the chunk dial in steps against your own traffic. Set max sequences to match the memory you really have so you pull people out of line less often, and pick a scheduling policy that fits your traffic instead of leaving the default on. You can run this yourself, standing up nodes, configuring vLLM, owning the autoscaler, and tuning, rechecking all of it every time traffic shifts. That's a system with an owner and a pager, and for a lot of teams, that's exactly right. Or you evaluate a managed layer that already staffs the lanes. So let's not just talk about it, let's run the same bursted replay from earlier against both and look at the tail. The reason I would weight DigitalOcean's dedicated inference here specifically, it runs vLLM with a prefix-aware router underneath, behind an OpenAI compatible API, so the interleaving and routing are handled instead of built back to US work. The prefix-aware part matters for the cart problem directly. If a new shopper walks up with the same list as someone already being served, it routes it into the lane that's already half rung up instead of starting from scratch. What's the prefix cache hit row above? That's the mechanism showing up in the tail. Whether the trade-off is worth it depends on your constraints. If you have got the team and the pager, self-hosting with chunk prefill tuned to your traffic gets you the most of the way. If you would rather not staff the lanes, that's what a managed layer is for. The whole video in one line: tail latency is not a hardware problem you buy your way out of, it's a line management problem. The average is comfortable, but the tail is where your users live. Measure the tail, ring up the big cards in chunks, and change one dial at a time. If you want me to take this multi-node, splitting the cart handlers and the quick lanes into a different machine, that's a whole new different topic on disaggregation. Drop a comment below and I'll see you in the next one.